welcome back to Beyond Compression, the podcast where we explore the technologies, strategies, and real-world challenges shaping industrial compressed air systems. I'm Pam, your host for today's episode. When a plant operator or EPC teams begin evaluating a new compressor, it can be tempting to start by comparing models, horsepower, and quotations. But in reality, some of the most important decisions must be made before any equipment is selected. And today we'll be talking about how to develop a strong compressor specification and why getting the specification right can have such a major impact on project execution, reliability, energy efficiency, and long-term performance. Joining me is Zach, one of our associate product managers. Zach, thanks for being here.
Thanks, Pam. I'm glad to be here.
Let's start with the big picture. When we say compressor specifications, what are we really talking about, and why does it matter so much?
Really, the specification is what translates the plant's operating needs into engineering requirements the manufacturer can use. Flow and pressure are part of it, of course, but they're only the beginning. We also need to understand the full operating range, gas conditions, site environment, available utilities, driver, the controls, and how the compressor connects with the rest of the plant. Those details influence nearly every part of a centrifugal compressor, from the aerodynamic stages and impeller design to the bull gear and pinion arrangement, coolers, lubrication system, driver, instrumentation, controls, and overall package layout. And the impact goes beyond the equipment itself. The specification can affect performance, efficiency, reliability, energy consumption, expected equipment life, commissioning, plant integration, project schedule, installation costs, and total lifecycle cost. Even what appears to be a small change in the process data or site requirements can change the compressor configuration, required power, or operating range. That's why having accurate information up front is so important.
So the specification is really shaping the equipment, not just documenting what someone wants to purchase, right?
Exactly. It translates the plant's operating needs into engineering requirements the manufacturer can use to design and price the right package. A strong specification also helps the owner, EPC contractor, procurement team, and compressor manufacturer stay aligned. So everyone is working from the same assumptions, which reduces the risk of surprises during proposal evaluation, order execution, or even startup.
Now, can you review which information is required to properly specify a centrifugal compressor?
Yeah, absolutely. And the first important bit of information needed is the process data, which is the starting point. At a minimum, we need to define the required flow range, inlet pressure, inlet temperature, gas composition, or molecular weight, and required discharge pressure as well as any other performance requirements. We should also identify off-design or alternate operating cases, since a compressor may need to operate under different seasonal conditions, production rates, or pressure requirements, and those cases need to be evaluated during selection rather than discovered after the design is already underway. Beyond the process conditions, the project team needs to define the site and ambient conditions, and these need to include minimum, normal, and maximum ambient temperature, along with cooling water temperature and available pressure, ambient pressure, relative humidity, and expected inlet filter pressure drop. The driver and electrical requirements are equally important, along with controls, instrumentation, testing and documentation, and future possible expansion plans.
You mentioned process data as the starting point. Why is that information so critical to compressor selection?
So, centrifugal compressor performance is tied directly to the gas conditions entering the compressor and the pressure the machine must produce. And the inlet pressure, temperature, flow, gas composition, molecular weight, and discharge pressure determine the aerodynamic design, stage configuration, power requirement, and available operating range. For example, a change in inlet temperature or molecular weight can affect gas density. That can change the actual volume entering the compressor, the work required by each stage, and the overall power demand. Even the definition of flow matters. Standard flow, normal flow, actual flow, mass flow, and inlet cubic feet per minute are not interchangeable unless the reference conditions are clearly defined.
So, two people can be looking at the same flow number but still be talking about two different operating requirements.
That's right, and that misunderstanding can lead to incorrect sizing. It's also one of the reasons we developed the AeroSwap Flow unit conversion tool. It helps users convert compressor flow between different units and operating conditions so they can compare performance on the same basis.
So what happens when the process data is incomplete or inaccurate?
The consequences can range from proposal confusion to real operating problems. The compressor may not cover the required flow range. It may require more power than the selected motor can provide. The discharge pressure may not be achieved under the worst-case ambient condition, or the selected package may include unnecessary margin that increases capital cost and reduces efficiency at the normal operating point. Incomplete data also creates more clarification cycles during the bidding process. Suppliers may make different assumptions, so proposals can look comparable on price, but are actually based on different technical scopes. If the process conditions are corrected after equipment selection, the project may require aerodynamic redesign, a different motor, revised controls, or other changes that can be both disruptive and expensive.
Thanks, Zach. Let's move into industry standards. We hear API 617 and API 672 mentioned frequently. What is the difference?
Good question. And the standards actually apply to different types of centrifugal compressor service. API 617 covers centrifugal compressors used in critical process gas applications, such as refinery, petrochemical, LNG, and industrial gas facilities. And the API 672 standard applies to packaged, integrally geared centrifugal air compressors used for plant air, instrument air, and process air in petroleum, chemical, and gas industry services. And it covers the compressor, the gearbox, bearings, lubrication system, the controls system, intercoolers, base plate, and testing and documentation. For air compressors that are integrally geared, API 672 is generally the appropriate starting point rather than applying the more complex process gas requirements of API 617. Applying the wrong standard can add requirements that don't improve the equipment but do increase cost, complexity, and lead time.
Another term we are hearing more often is JIP 33. What is it, and how does it affect compressor specifications?
Yeah, that standard is coming up in more projects. JIP 33 is an industry initiative led by the International Association of Oil and Gas Producers to standardize and streamline procurement requirements. Historically, suppliers could receive hundreds of pages of owner-specific requirements for each project, with different formats and expectations even across projects from the same organization. That created a lot of extra work for owners, EPCs, and manufacturers. The way it works is that JIP 33 builds on established industry standards and organizes procurement requirements into a supplementary technical specification, information requirements, quality requirements, and a procurement data sheet. And for centrifugal air compressors, the applicable overlay is IOGPS 612, which builds on API 672. The goal is to reduce specification variability, improve project predictability, and strengthen cost control. At FS-Elliott, we've completed projects for JIP 33 applications and can help advise on these requirements.
You mentioned unrealistic assumptions earlier. What are some examples you see in specifications?
Ambient conditions are a big one. Sometimes extreme temperature, humidity, or dew point values are carried over from a general site standard without confirming that combination is realistic at the compressor inlet. For example, API 672 specifically notes that a dew point above 33 degrees Celsius or 92 degrees Fahrenheit are uncommon, and anything above that shouldn't be used when defining operating conditions. So, designing around unrealistic combinations of maximum temperature and humidity can affect intercooler sizing, condensate calculations, power, and package cost.
Okay, that was a great overview of those standards. Now let's talk about the driver. Why should motor and electrical requirements be established early?
Yeah, the driver is one of the most significant components in the package, and electric motors are often among the longest lead time items. The specification should define the voltage, frequency, enclosure, insulation, and service factor, and also the starting method, hazardous-area certification, and any site or owner requirements. A late change in voltage, classification, or motor standard can require a completely different motor design. That can affect the base plate, coupling, electrical system, and even controls, testing, and delivery schedule. And another important consideration is motor sizing. While many standards call for oversized motors under certain conditions, that extra capacity often provides little real-world value and can reduce package efficiency while increasing overall costs. The starting method also matters. Across the line, reduced voltage, soft starter, and variable frequency drive arrangements have different electrical and mechanical implications. The plant power system must be able to support the selected approach. And if a steam turbine or another driver is being considered, the available steam conditions, speed range, governing philosophy, and applicable driver standards need to be defined just as carefully.
And how does hazardous area classification influence the package?
Area classification affects motors, instruments, junction boxes, and control enclosures, and also wiring methods, heaters, lighting, and many other electrical components. And a package designed for an unclassified area can be very different from one required for a Class 1, Division 2 area, or an IEC zone classification. The project also needs to identify the gas group, temperature class, and certification requirements. Simply stating that the area is hazardous is not enough to select compliant equipment. Because these requirements affect so many purchased components, discovering them late can create significant redesign and procurement delays.
Okay, now let's move on to controls and instrumentation, which are another major part of the specification. What decisions need to be made early?
The controls need to align with the plant's overall automation strategy. That includes surge avoidance or anti-surge protection, DCS and ESD integration, communication protocols, remote monitoring, instrumentation, alarm and trip philosophy, cybersecurity and redundancy requirements for power, controllers, and communications. The manufacturer needs to know which functions will remain within the local compressor control panel and which signals or commands will be exchanged with the plant DCS and ESD systems or the motor control center. Communication protocols such as Modbus TCP, Ethernet IP, or other plant standards should be identified, along with expectations for hardwired signals and time synchronization.
You mentioned anti-surge protection, which is often described as one of the most critical control functions. Why is it so important?
Yeah, so surge is an unstable operating condition that can occur when compressor flow falls below the stable operating range at a given pressure ratio. During surge, flow and pressure can fluctuate rapidly, and repeated or severe surge events can damage the compressor and connected systems. An anti-surge system monitors the compressor's operating condition and opens an unloading or recycle valve before the machine crosses into the surge region. That's why anti-surge requirements need to be considered as an integrated system rather than treated as one-line item on an instrument list.
Can you explain some of the protection and monitoring capabilities available through our Regulus control platforms?
Absolutely. We offer configurable control solutions through the Regulus R2000 and R3000 platforms. Depending on the application, available capabilities can include our standard surge avoidance logic, anti-surge control, integrated compressor control, and pressure band optimization. Also, Energy Advisor, maintenance notifications, and FS Connect remote monitoring. For demanding engineered applications, the R3000 can incorporate redundant power and communications, advanced machine monitoring, alarm and trip voting logic, auxiliary system controls, and enclosure options such as NEMA 4X stainless steel or hazardous area rated designs. The goal isn't to add complexity just for the sake of it. The control system should provide the protection, visibility, and plant integration the application requires while remaining understandable and maintainable for the people operating the equipment.
That last point is important. A specification can become extremely detailed. How do teams avoid over-specifying the package?
Every requirement should connect to an operational, safety, regulatory, or reliability objective. Specifications often collect requirements from old projects or multiple corporate standards and several API documents. Over time, duplicate or conflicting provisions can remain even when they no longer fit the actual application. The answer is not to remove rigor, it is to review the requirements deliberately. So it's important to ask whether the plant is properly spared and confirm the actual area classification, and verify the environmental conditions. Identify which instruments truly require redundancy, and determine whether a special test or document will influence acceptance or future maintenance. That approach helps preserve the requirements that add value while avoiding unnecessary package complexity, cost, and lead time.
Can you tell us about some of the most common late-stage changes that can create project problems?
Sure, some changes have a greater impact than others, including revisions to flow or pressure, motor voltage, or changes to hazardous area requirements. Also, changes to DCS integration, cooling water conditions, or testing and documentation requirements. Most of these changes are manageable when they're identified early, but once equipment has been selected and purchase orders are underway, the same changes can trigger engineering rework, revised drawings, added costs, and schedule delays.
So, how does early collaboration reduce those risks, and where does FS-Elliott fit into that process?
Early collaboration gives the owner, EPC, and compressor manufacturer a chance to align before the specification is finalized. It allows everyone to confirm the operating conditions, resolve conflicting requirements, identify long lead items, and agree on the control approach while changes are still relatively easy to make. At FS-Elliott, we support that process by reviewing operating conditions, interpreting industry standards, identifying potential conflicts, and evaluating package options. We've also developed standardized tools and documentation for API 672, API 614, and JIP 33 projects that clearly communicate our proposed scope and any clarifications. The goal is to help everyone make informed decisions early, provide recommendations to improve performance, and keep the project moving in the right direction without overpaying for unnecessary equipment.
If you had to narrow it down, what are the most common specification mistakes you see?
A few come up repeatedly, such as providing only one operating point without defining the full required range, using unclear or inconsistent flow reference conditions, and applying the wrong API standard to the service. A few others we've seen are specifying special duty without evaluating system sparing and criticality, and carrying unrealistic ambient conditions into the design. Also, leaving motor, electrical, or hazardous area requirements unresolved, and treating controls and anti-surge protection as late-stage details are other common mistakes. And lastly, and very important, combining owner standards without resolving conflicts, focusing on purchase price without comparing efficiency and lifecycle scope, and waiting until after equipment selection to involve the compressor manufacturer. The good news is that most of these issues are preventable. The common thread is simply getting the right people involved early enough to clarify the technical basis.
For someone who is beginning a new compressor project, what practical steps would you recommend?
The first step is to define the real operating need, confirm the normal, minimum, maximum, and future flow requirements, along with inlet conditions and discharge pressure. Then document all expected operating cases and identify which conditions must be guaranteed. Confirm the site utilities, ambient conditions, cooling water and electrical system, and also the driver requirements and hazardous area classification. Select the appropriate industry standard and duty classification based on actual service and sparing philosophy. They must also establish the control, instrumentation, communications, cybersecurity, and plant integration requirements, and identify inspection, testing, and documentation and quality requirements before the RFQ is issued. And finally, involve the compressor manufacturer early enough to review the technical basis and identify issues while they are still easy to address.
Before we wrap up, can you share an example of a project that illustrates why getting the specification correct upfront matters?
One project that stands out involved a large expansion facility with API 672 requirements. We worked closely with both the EPC and the operator during specification development, which helped keep the project on schedule and avoid unnecessary costs. One challenge was integrating the customer's DCS with the compressor controls. The two systems needed to exchange information, including interstage temperatures, motor current, and equipment diagnostics every few milliseconds. Instead of waiting until startup to address compatibility issues, our control engineers worked with the customer early to define exactly how the systems would communicate. The package control system also included redundant processors, power supplies, and input-output modules, and smart transmitters provided operators with valuable diagnostics while filter monitoring tracked differential pressures to help maintenance teams identify issues before they became problems. A dedicated project engineer kept everyone aligned through regular meetings and 3D model reviews at the 30, 60, 90, and 100% milestones. During one review, it became clear the originally requested baseplate supplier would create unnecessary complications. By evaluating qualified alternatives early, the project avoided delays and additional costs without compromising quality. And once manufacturing was complete, the compressors completed full speed and full load factory acceptance testing in accordance with API 672 and ASME PTC 10. The bearings, seals, and rotating components were also inspected, giving the EPC and operator the confidence that the equipment met the specification before shipment. And looking back, one of the greatest benefits wasn't simply successful testing, it was that the customer avoided costly engineering changes after manufacturing had started because requirements were identified early. And because of this, the project reduced redesign work, minimized change orders, stayed on schedule, and entered commissioning with confidence. And that's exactly what a well-developed API 672 specification is intended to accomplish.
Thanks, Zach. But before we close, can you summarize the main takeaway for our listeners?
Yes, of course. The most important thing is to understand that a specification is not just a document used to obtain pricing, but it's the engineering foundation for the compressor's performance, reliability, controls integration, project cost, and long-term operation. And having complete process data, appropriate standards, early decisions on drivers and controls, and collaboration among the owner, EPC contractor, and manufacturer can prevent costly late-stage changes and improve the final project outcome.
Zach, thanks for joining us and walking through the key decisions involved in specifying a centrifugal compressor.
Thanks, Pam. It was great to be here.
And thanks to everyone listening to another episode of Beyond Compression. Whether you're developing a new specification, reviewing an EPC document, or evaluating compressor proposals, remember that the decisions made early in the project can affect reliability, efficiency, cost, and performance for years to come. To learn more about FS-Elliott's air and gas compressor solutions, or to connect with our team about an upcoming project, visit FS-Elliott.com. And don't forget to follow us on LinkedIn and Facebook for future episodes, engineering insights, and industry updates. Until next time, thanks for listening, and thanks for letting us be part of your journey towards smarter, more efficient, and more reliable compressed air systems.